I'm going to go ahead and start recording.
Yes, ma'am.
Get started. Anybody have any questions before we start?
No, I don't think I have a question. Well, I just have a question if you received my PDF file.
Did I not send you an email back?
Um, well, I don't think I got one back. I'll double check, ma'am.
Okay, because most all of the ones that I got, I sent an email and said that I hadn't received them. So if you didn't get an email saying that, let me know so I can check.
Yes, ma'am.
Okay. I'm gonna get just a minute for anybody else to join because I had the wrong time on here. I guess I had 1 o'clock instead of 9:30. Oh,
Yes, ma'am. I don't think I received an email from you back.
okay. Is this Mark?
Yes, ma'am.
Okay, I'll check. I'll check and see if I have one on there. I
Yes,
may
ma'am.
have just missed.
Yes, ma'am. Thank you.
All right. So I don't forget. No problem. Those of you who think it's a good idea because then you can ask me directly and we can be in contact. All right. Well, I'm going to go ahead and share files and take it a minute. My internet is slow this morning. I had a conference call this morning with the president and all those guys talking. So looks like we're definitely going to have online for the summer. So if you are interested, especially in taking Chem 2, you should go ahead and sign up for it. And it looks like we will be doing it online. So if you're willing to do it online, then it'll be a good time to do it because it'll probably be the only time we ever offer it online. All right, so we're going to do chapter 9 this morning, and it's actually just the first part of it. And the chapter 9 is thermochemistry, and then we're going to end the course with chapter 10, which is gases. So we'll do part 1 of chapter 9 today, and then Monday we'll do part 2 of that, and then we'll do chapter 10, parts 1 and 2, and then we'll have a review, and then you'll be ready to take that last exam. And so just like the previous one, you've got lots to do, and I should have all those taken care of. I worked this over the weekend and tried to get all the labs figured out and the quizzes in there. So everything should be loaded into Unit 4 except for the exam 4, which I still have to convert. But other than that, y'all should have everything that you need. So if you're missing anything or you notice anything, just please let me know. All right, so we're only doing the first half of chapter 9. We actually cover the second half of this in Chem 2, and so they overlap a little bit. I do bomb calorimetry in both of them, but we're going to look at the different units of energy. We're going to look at how energy flows into and out of a system. We're going to then do some calculations based on that and temperature change. And then we're going to calculate the energy transfers within this bomb calorimeter, as we call it. So the nature of work is this is just the general information that we're going to go over first. All right, and so energy is anything that has the capacity to do work, and to do work you have to apply force over a certain distance, and basically you're going to move an object a certain distance across something or whatever, so you apply that force, And so that's why energy is considered to be work times force, or work, or, sorry, get my pen ready, force times distance. Heat is something that goes along with work a lot of times, and that's the flow of energy caused by a change in temperature. And so heat and work are basically one of two things you're doing within a system. You can exchange heat. You can exchange energy by heat transfers, or you can exchange energy by applying work to something. And so between the two of those, basically we have that energy flow. So the two types of energy, I'm sure you remember this from high school, is there's kinetic energy and thermal and potential energy. And kinetic energy is energy of motion, or you're actually using the energy. And thermal energy, the energy associated with heat, is one way that we can see energy applied in a system. And thermal is kinetic energy, and so when you produce thermal energy, you're producing kinetic. Potential energy is stored energy, as I said, and so that's the potential you have, or that's how much energy you have stored in something, okay? And chemical energy, or the energy that we store in the structure of a compound and within a bond between two atoms, is potential energy. So basically, the kinetic energy is motion, energy in motion, okay? And one type is thermal energy, and then potential energy is only due to what the composition of something, or where it is. How high it is up on top of the hill determines how much potential energy you have, okay? Also, what type of bond you have between two molecules can determine how much or what type of potential energy you have. All right, and so just having something tied together is a stored energy, because it took energy to make that bond. So when you break the bond, you release whatever energy it took to make it in the first place. So other forms of energy are electrical energy, which is kinetic, and that's the flow of the electrons. Light energy, which we saw earlier in the semester, and that's energy transfers based on the atom and how the electrons are moving. Nuclear energy is the potential energy that's stored within the nucleus. And then finally, as we said, the chemical energy is what we have stored between atoms, and it's relative to their position and what type of bond they have, whether single, double, or triple. So our units of energy, kinetic energy in physics is defined as 1/2 mv squared. So mass times velocity squared, okay? That's another one of those we get from Einstein. We use, as far as units go, the joule, okay? And the joule is the same as a Newton meter in physics. And the other we use sometimes in chemistry is kilogram times meter squared per second squared. Those are equal, okay? 1 joule is equal to a kilogram times meter squared per second squared. We don't typically use the Newton meter. That's more used in physics. By definition, a joule, how much energy it takes to 1 kilogram mass 1 meter per second. So that's why these are basically the same. A calorie, that's a little see how much it would take to raise the temperature of 1,000 water 1 degree C. And the kilocalorie are so these are some that you may use. There are, in 1 small calorie, there are 4.184 joules. Okay, so in a kilocalorie, you have 1,000 calories. The food calorie, as I said earlier, with capital C, that is the same as a kilocalorie. And then kilowatt hours, we don't use those in chemistry so much, but in electrical work, a kilowatt hour is 3 times 10 to the 6 joules. So these are just the basic conversion factors that you might be using when you're doing conversions in energy. So when we talk about thermodynamics, we're talking about the study of energy and how it one form to another. And we study how one form of energy to another because they follow the first law of thermodynamics, which is the conservation of energy. That means you can't create or destroy energy. So since you can't create or destroy, you only change it from one form to the other, and so it is conserved. Okay? That's the conservation of energy. When it's conserved, that means that you don't lose within the universe. Okay, so if you increase energy in a system, then you must decrease the energy in the surroundings, and so you have to have an equal one-to-one change between those two things. So when we talk about energy, we talk about the system versus the surroundings, and I always draw a little bucket when I'm thinking about this. Okay, and so inside here is my system, and then everything outside the system is the surroundings. Okay, and so when I'm looking at this really small area. Okay, I don't really think about the universe that much. That's for, you know, physicists and things like that. But the system is the part of the universe that you're studying, and then the surroundings is everything else in the universe. So everything outside the system that you can exchange energy with. And so whatever you're doing in here, boiling, whatever, inside your system, then you have something going on out here too, which is your surroundings. So energy can flow into the system, or it can flow out of the system either way. So it depends on what you're doing in the system. So if the energy drops inside the system, then if you drop the energy, you decrease the energy inside the system, that means you're going to increase the amount of surroundings. So it has to get off energy out of the system. That means it's exothermic. Energy flows into the system, surroundings. Surrounding decreases because energy from the surroundings and put it into the system. And so that would be an endothermic reaction. And so this is just some things about talking about conservation of energy, just a few more details about that you don't gain or lose the energy. You just typically are exchanging it for different forms, including heat. And you can, you know, it can be converted to heat, which is another form of energy. So the way energy flows, since whatever I put into the system has to leave the system, then the overall change in energy of the universe is going to be 0. So the change in energy of the system plus the change in energy of the surroundings is also 0. And so we can look at that by saying the final amount of the energy in the system minus the initial amount gives us that change in energy. So it's really hard to measure changes in internal energy. Okay, it's a state function. There's a lot of things going on in there. The internal energy is the sum of all the energies going on, the kinetic, the potential, the heat, everything, of all the particles that are in the system. And so since it's a state function, I don't really have to worry about what's going on with all the details inside. I just need to know what the initial and the final energy is. So if I know the energy of the products minus the energy of the reactants, that's going to give me the change in energy of the reaction. So even if I don't know the exact energy levels that everything is, I can calculate the difference. And by calculating the difference, since it's a state function, that's all that really matters. So the analogy in your book is if you were going to climb the top of Kilimanjaro, and there are a couple. One straight up the mountain is mountain climber people. It's 5 miles, okay, and you from 0 to 1,000 feet elevated. It takes you 5 miles to get there. It's not as difficult. More people can actually do that and get to the summit, but it takes 12 miles to go 10,000 feet. So it doesn't matter that it took you 5 miles or it took you 12 miles of walk there. Your change was from 0 to 10,000 feet. So basically those are the same from the state function, because you're only looking what the difference was in elevation. So it just matters how high you went. It doesn't matter how you got there. And so that's what we were saying is going on with the energy. And we've seen energy diagrams before when we were looking at reactions with electrons and things like that, where things go up and then they come back down. So kind of the same thing happens in a reaction. Is if you have carbon and oxygen and they react together to form CO2, the reactants come together and form a lower energy, more stable product. And when they do that, the change in energy is negative, because you went from energy up here to energy down here. And so the difference is a negative number, or less than 0. So that is an exothermic reaction, because you gave off energy to get to a lower energy. So when you're looking at a system and a surroundings, if you take the energy of the system and you're flowing energy out of the system, your energy is going down, so you decrease the energy in the system. If you decrease the energy in the system, it's got to go somewhere, so it's going to increase. Okay, and then vice versa. If you take it from the surroundings to the system, you decrease the energy in the surroundings as you increase the energy in the system. And then, as I said, if you started out at a lower energy with your reactant and ended up with a higher energy in your products, that means that you put energy in, right? And so you're going to have more energy in your products than you did in your reactants. And so the change in the system is going to be positive this time. And because of that, it's going to be negative. You're going to remove it from the surroundings. So basically what I'm saying here with these energy diagrams is, if the reactants are higher in internal energy than the products, then the change in energy is negative because energy flows out of the system to the surroundings. If your reactants have a lower internal energy than the products, then that means that you flowed energy into the system in order to make that reaction occur from the surroundings, and then you are going to have a higher change in energy, or delta E. So the internal energy, basically, if energy flows out, you're taking it out. If energy flows in, you're taking it in, and you are increasing that amount of energy. So I've said this a whole bunch of ways. So the way you apply this is that if you have, for example, 1,200 joules of heat, so I'm going to draw my system, and I told you always you can draw a box or a bucket or whatever you want to do, right? If 1,200 joules of heat are added to a system, so you know this is my system, and everything is outside this is the surroundings, okay? And it keeps on going to the universe. All right, and I'm adding 200 joules to the system, and the system does 800 joules of work. So if it does work, that means it's using energy. So that means it's getting rid of 800 joules of work on the surroundings. So what is the energy change? Well, so energy change is you brought in 1,200 joules and you used 800 joules. So the change in energy is a positive 400 joules. So the system ends up with 400 joules when all that is done. Now, so after what I said about system and surroundings, that's pretty easy math, right? So this is the same thing. Okay, so I'm going to just redraw it a little bit. All right, so I took 1,200 joules from the surroundings, all right, and then I added work to the surroundings of 800 joules. So this time I took 1,200 joules from the surroundings, and then I added 800 joules to the surroundings. So my change in energy is a negative 400 joules on the surroundings. And this is always true, okay? Whatever you've taken from the surroundings, you're going to add back. Whatever you add to the surroundings, you're going to have to take from the system, because you're only exchanging between the system and the surroundings. All right. So that's really all I'm talking about today, is these changes in changes in energy, and that it's understand that you know how that flows, and anytime you increase the energy from the system, you're going to decrease energy of the surroundings. And you have another practice problem where it's asking you, and it says in your practice problem, it says you start out at E1. Well, E1 just means that's whatever that energy was in the system, even you don't know what it is. And so they're asking you, what is the change? Does it change? Does it go up so much? Does it go down so much, or whatever? And so when you're looking at changes in internal energy, then that's really all you have to do. So you kind of need to go through that a little bit so that you can understand what's going on with that. So I just want to go on a little bit, since this didn't really take a long time, and talk just a little bit more about these energy exchanges. So energy exchange between the system and the surrounding can either be work or it can be heat. Okay, it can be work or it can be heat. And these are not state functions. And so they do depend on what's happening in the system. And so if I want to know the change in energy, I can measure both of those things. I can measure the amount of work and I can measure the amount of heat. So if Q is positive, that means that I'm gaining energy. And I'm always talking about system, okay? So if I'm just in general talking about it, I'm talking about the system. Unless I specifically say what happened to the surroundings, then you can assume safely that we're talking about the system. And so if Q is positive and W is positive, you gained thermal energy and you did work on the system. And the delta E is going to be a negative. If you lose energy, it's negative. If you do work by the system, okay, or do work on the surroundings, that decreases that energy that's in there. And so you're going to have an overall negative energy flow from the system to the surroundings. So you've got to look at words in these problems that talk about you did work on something, okay, or work was done by something. And so you've got to interpret which thing is working, and so which thing, system or surrounding is going to go down in energy level. So some of these, look at all those words, I know. Some of these are pretty wordy, but we've learned by now that we can kind of go through these and we can pull out the numbers that we need to know. So the first part of this is talking about firing a potato cannon, and you have a certain amount of work associated with that or whatever, and it says, once you do this, it ignites and blah, blah, blah. Okay, so, and that's why I underlined some things, because I wanted to just draw your attention to this and how we're reading these word problems. It says the cannon emits heat to the surroundings, okay? So that tells me that that is going to be leaving the system, because the cannon is the system, right? If the burning of the fuel performs 855 joules of work on the potato and produces 1422 joules of heat, what is the delta E for the burning of the fuel? And it says don't try this at home, okay? Although lots of people do. You can go on YouTube and watch them do these potato cannons. It's pretty funny. So the delta E is going to be defined as the heat plus the work. And so where the sign comes in is what happens in the system to this. And so you got to really read these, okay? So it emits heat. So I know, since it told me that it emitted heat, that's going to be a negative. Oh, do you really? Sorry, wait, hang on. All right, Nathan has one in his basement. Yeah, you can definitely break some stuff with them. They can be pretty powerful. So a negative 1422 joules. I'm calling that negative because I say it emits the heat to the surroundings. So I know that's going to leave the system. All right, so in my system this time, all right, I have the cannon. I'll just do it like this. It's kind of like a tube. And I've got the potato in there, okay, right? And then I've got some fuel. All right, so that's kind of my system. And it says I emit this 1422 joules. All right, and it says that it performs work on the potato. Where's the potato? It's in the system, okay? So since the potato is in the system, I'm performing work on the system. So that's another negative 855 joules. So the overall change is a negative 2277 joules. So you've got to really think about what's going on. That's why, I'm visual, that, but that's why I draw it, because it reminds me what's in the system, what's out of the system. Because when you go to assign these signs, which makes a huge difference on the answer you get, you've got to be able to figure out, did the system lose energy because of whatever that was, or did it gain energy because of whatever that was? And so then you have one that's similar to it here. And you do have one or two on the test, so make sure that you can kind of decipher that. And I think there's some mastering problems that address that as well. Okay, so I am going to stop here. We'll come back to heat exchange when we come back together on this. So any questions on this kind of introduction to thermochemistry? Okay, I assume everybody saw the revised schedule and the revised lecture series. I've got the dates on there for you with the right time, and I'm going to go back and change the times for all of these. We have a couple of weeks before we take the test over this. This is the last semester of this. If you missed anything in Unit 3, since it was the first time we've done this, you can still go ahead and complete those assignments, but you've got to email me and tell me what you did and when you did it, because I have to go back and hand grade that stuff. It doesn't necessarily tell me if you've done it. So it's very important that you let me know when you do something, if it's past the deadline. I'm being a little generous with it, because especially this past unit, because I know that this is new to y'all and y'all didn't sign up for online. I didn't either. But we've got to get this done. We're all having to do our part in this. I have a really good friend who has it, and they're in another country right now in a hospital. So everybody's probably at some point going to know someone who's been affected by this. And so this is how we are helping everybody, is by doing our class online. So do your part, stay home, be safe. All right, any questions about the schedule or assignments or anything like that?